Math and Beats. In this video, we are going to go over what's called unions, intersections, and complements of sets. Let's go. All right. First of all, what are these things? Little setup here. We're going to let A and B be sets. And then we're going to define each of the following ways to combine these two sets. And we're going to show some diagrams to help us visualize what's going on. And in the diagrams, we're going to look at the shaded regions are what's going to represent the relative combination that we're talking about. So we got these two sets, A and B. We can take the union of A and B. So I guess I'll just show you the picture at the same time. And the union symbol here, A union B as we say, where that symbol, have a big U looking symbol, stands for union, go figure. It is defined to be the collection of values, say x's, so that x is an element of A or x is an element of B. So look at the diagrams below. Let's just visualize each of those circles there to be what's in set A or what's in set B, each circle representing that set accordingly. And you say, well, what's in A or what's in B? So that's not saying that we have to have them at the same time. We're just saying you either have stuff from A or you have stuff from B. Now, there might be stuff that's also common, and we just don't count that twice. So you say, what's in A, what's in B, or what's in both. So when I take the union of two sets, A and B, we get the collection of all the values that are coming from A or B or both. Now compare that to the intersection of the sets A and B. Intersection. Here's our notation. A intersect B. So that symbol is basically the union symbol flipped upside down. That's your intersection symbol. What does it mean? It's the collection of all values, say x again, so that x is in A. It's an element of A. Now, importantly here, and it's in B. So it's got to be in both at the same time. Where is that in our shaded region here? Everything that's simultaneously both in A and in B. So that's the intersection. We've got the union and the intersection down. And then one little note here that if you happen to have a situation in which the intersection of two sets is the empty set, remember the symbol down there, empty set. So if the intersection of them is the empty set, then what's that really saying? It's saying that the two sets, A and B, have no elements in common. And in that situation, some vocabulary, we say that the two sets A and B are disjoint. So just remember that vocabulary word. It can happen. How about the complement? Complement of B in A, denoted here by this A and then like this slash looking thing, B, almost like a fraction symbol. Or just, you could also say A complement B, the complement of B in A. And what is that? It's the collection of everything that's in A, but is also not in B. So in the diagram we see below, where is that shaded region? Right there. That's all of the elements that are in the set A, but are not in B. Right? If it was also in B, it would occur right here, but that's a big no-no because we don't want it to be in B. Even though it was in A, we exclude all the B values and obtain only what's in A and not in B. The complement of B in A. So that's how we define these combinations of sets. Let's look at an example. In this example, we have three sets here. Set A, just 1, 2, 3, 4, 5. Set B, 2, 4, 6, 8, 10. And then finally, set C over here, which is the collection of values, column x's, that are integers, right? X is an element of Z. X is an integer. And then X is between -2 and 8, including the -2 and the 8. So if you literally wanted to write that out in listings notation, you could. It would just be a little bit longer. It'd be all the numbers, -2, -1, 0, 1, 2, 3, ... all the way down to 8. So we got these three sets, A, B, and C, and we're going to find each of the following. First, we're going to look at the union of A and B. So remember what that is. Everything that's in A, or that's in B, or that's in both, without counting elements twice. So let's go through and dissect this statement here. The union of A and B, like I just said, is the collection of x's that belong to A or belong to B. That's like saying X is in A or X is in B. What's that the same as saying? Either X is coming from the set 1, 2, 3, 4, 5, that's set A, or X is coming from the set 2, 4, 6, 8, 10. That's your set B. So we just got to find all different elements that we see out of all those sets. What is it? There's a 1. There's a 2. Notice that 2 occurs in both A and B. There's a 3 coming from A. There's a 4 common to both of the sets. There's a 5. And then there's a 6, 8, and a 10. The union of A and B in this situation. You probably can guess what's coming next. Ah, yes, the intersection of this time A and C. So A was 1, 2, 3, 4, 5. And then remember, C was all the integer values between -2 and 8 inclusive. So let's dissect again. The intersection of A and C is the collection of values that are in A and also in C. That's the same as saying X is in A, or, and X is in C. So X is either in A, that we got right here, and it's got to be in C. So we're just looking at the values that are both in A and C, common to both sets. So it can't be a negative number because there's no negative numbers in A. It can't be 0. 0 is not an A. So it's got to be coming from these values right here, 1, 2, 3, 4, 5. And in fact, 1, 2, 3, 4, and 5 are all in the set C. So hence the intersection here, what's common to both of those sets, is actually the set A. A is really just a subset of C here, proper subset. And so the intersection of A and C is just the set A because that's the elements that are common to both. How about something else? How about if we took all three of the sets and we union them in part C here, A union B union C. So that's like now saying X is in A, or X is in B, or X is in C, or it could be in all of them at the same time. So X is in A, or X is in B, or X is in C. So X is either coming from the set A, the set B, or the set C. So we got to just take all the elements that we see out of all these sets and list all the different elements. What are they? Well, in C, there's -2, -1, and 0. Those three numbers are neither in A nor B, but they're in C. 1 is common to A and C. And then the number 2 is actually common to all three sets. 3 is in A and C, not in B. 4 is common to all of them. 5 is in A and C. 6 is actually in B and C. 7 is only in C. 8 is in B and C. And then 10 is also in B. So all those numbers, the union of all three of the sets. So you could take unions and intersections of however many sets is needed. How about the intersection of all three sets? A intersect B intersect C. Now we're saying what is an A, B, and C all at the same time? So that's like saying X is in A, and X is in B, and X is in C. X is in A, and X is in B, and X is in C. Here's A, here's B, here's C. What are the common elements to all of those? Well, it's got to be even number because B only has even numbers. It's got to be positive because A only has positive numbers. And then C, of course, has all the values of X less than or equal to 8 and greater than or equal to -2. So what are the common numbers that we see in all three of the sets? 2 is in all of them, right? 2 is in C over here. And then 4 is also in all of them. But then once we get larger than 4, right? 5, 6, 8, and 10, those numbers are in multiple sets, but they're not in all of them at the same time. So that's it. It's just the elements 2 and 4. What's common between all three sets, the intersection of A, B, and C. Now, I don't have a complement problem pre-written, but we can make one up. How about part E here? Let's find A complement B, or equivalently, the complement of B in A. Remember what A was. A was the set 1, 2, 3, 4, 5. And B was the set 2, 4, 6, 8, and 10. Well, remember what this complement idea meant. It meant take away everything that's in B from A, and what are you left with in A? So obviously 10, 8, and 6 are in B and not in A. So we'll get rid of those. But 2 and 4, excuse me, clear my throat. Sorry about that. All right, 2 and 4. Notice they're in B and they're also in A. But because they're in B, we got to get rid of them. Exclude them from this complement. Hence, this complement here is just the set 1, 3, and 5. Because those are the elements in A, which are not in B. And then that's it. That's the video. So, some operations on sets. And stay tuned for the next video. And stay tuned shortly here for a short beat. Light